Speaker is
This meeting is being recorded.
right. Today's speaker is let me get rid of this thing. Oh, that's interesting. The mouse doesn't want to go on the relevant. Oh no, it's okay. It's not this way.
That's so weird.
Anyway, today's speaker is Ardith Bravenec. She's a postdoc here at she's been here since last summer, and before that she did her PhD at the University of Edinburgh in Scotland, and then before that she did a bachelor's degree at Millsaps College in Jackson, Mississippi, and she triple majored in chemistry, mathematics, and creative writing. So an interesting background. She also had a Goldwater scholarship as well as an undergraduate, which there aren't too many of those. And today she's going to mostly talk about stuff that she did during her PhD, actually, which is about, as the title says, magma, ocean crystallization, redox, and carbon oxygen hydrogen volatiles.
Great, thank you. Let me just make sure I can actually switch slides here. All right, awesome. So this talk is really going to be composed of three different parts. First off, I'm going to give you an introduction to some methods in experimental petrology, which was the primary technique I used to run these next two studies. The first one is going to focus on magma ocean crystallization and what happens to water and other important volatiles such as methane and hydrogen gas as these early protoplanets start to solidify. And then the third part of my talk is going to be on synthetic Martian basalts. So analog pieces of Mars that we've created in a laboratory and what they can tell us about the total Martian water budget in the interior and how we can back calculate that from using analyses from meteorites. To start off, I want to give you an overview of two really big topics that I'm going to talk about. And the first one is hot rocks. So as this quote says, everything has a natural explanation. The moon is not a god, but a great rock, and the sun a hot rock. And maybe this is a huge oversimplification of what planets are, but essentially from a laboratory perspective, from an experimental perspective, it's nice to be able to simplify these really complex systems down into little pockets of magma. So yes, I'm going to be talking a lot about tiny hot rocks. And in fact, I'm going to be talking about some elusive qualities of these hot rocks. So fugacity in a more literary sense means something that's fleeting, something that's gaseous, and something that quickly evaporates. But in the experimental petrology sense, in the thermodynamic sense, fugacity has a much more concrete and useful meaning. And that's what this poem is getting at. Fugacity has no memory. It has no past, only what it sees last. And in fact, much of what we know about magma oceans is not directly measured. Obviously, the Earth has solidified from a magma ocean. We no longer have those original measurements of what the fugacity might have been. And again, that's why it's necessary for us to do this experimental petrology work. So you might be asking yourself, what is a magma ocean? It's just as the name suggests. It's a stage early in planetary formation and evolution, right after the accretionary processes, when a planet is either partially or fully molten. And we think it's fully molten as a necessity after these really high impact, high energy environments condense. And why we care about magma oceans from an astrobiological sense is that these are really those initial conditions that set a lot of the habitability parameters, whether or not it forms an ocean, an early atmosphere, and it also affects a lot of the interior dynamics of the planet, perhaps even plate tectonics, volcanism, the rheology of the mantle, and so on. So those are some of the reasons why we care about magma oceans. They're supposedly widespread for all rocky bodies, and then they have many implications for the kind of planet that you get after. Okay, I mentioned volatiles before, and perhaps the most famous volatile that we all care about is going to be water. This is where it gets a little bit interesting though, because when I talk about water in deep planetary interiors, I'm not actually talking about the fluid water that we all consume on a daily basis. I'm actually going to be talking more about these dissolved water groups or these dissolved hydroxyl groups within minerals. And in fact, in the major phases of the Earth's crust, well, and mantle, and many other terrestrial bodies as well, those primary building blocks of the planet are going to be these nominally anhydrous minerals, olivine, pyroxenes such as clino and orthopyroxene, and then perhaps deeper down at greater pressures, garnet. Where there are other minor hydrous phases in the crust and mantle, such as melt, glasses, supercritical fluids, and then also in other minerals such as apatite, amphibole, serpentine, and so on. But from a planetary perspective, I'm really going to focus on these nominally anhydrous minerals, olivine and pyroxene. So then another big word that is going to be very useful in this talk is going to be fugacity. And simply put, fugacity is the corrected behavior for a non-ideal gas, where you typically get non-ideal behavior within these planetary interiors. So that is when you have very high pressure. They're still going to behave non-ideally, even if you have very high temperature. And we know this from just looking at the fugacities of individual gases and equation of state calculations of those gases, where you can see our really interesting volatiles, water, hydrogen gas, methane. They're all behaving non-ideally. We're not seeing that the pressure is directly equal to the fugacity. So the bigger question is then, how do these gases behave when you mix them all up together and when you put them in a real environment in a magma ocean, that is coexisting with the magma and then the solidifying crystals? And this is important because redox is really important in our solar system in between different rocky bodies. So you can see here that the Earth has a different redox state than perhaps Vesta, the moon, achondrites. Where if you work with geochemistry, you're probably very familiar with this, but we typically write redox state or oxygen fugacity relative to one geochemical buffer, which is the iron-wüstite buffer. And that's simply a redox equation between iron and iron oxide that's going to impose a certain amount of oxygen or hydrogen in the system, which imposes a certain redox state. And what's really interesting here is we expect magma oceans, those very primitive bodies, to be more similar to the solar nebula in terms of redox than to modern Earth. If you look here, Earth is considered relatively oxidized when you consider the scope of different redox states in our solar system. Okay, so this is how we actually study these things. This is a piston cylinder press, which is a high pressure, high temperature device capable of reproducing planetary interior temperatures and pressures. So in this case, that means up to about 4-5 gigapascals of pressure and around 1800 degrees Celsius. You can achieve higher pressures and temperatures in a laboratory, but the advantage of the piston cylinder press is also that it's a large volume apparatus, meaning I can get a lot of sample in here. And then that gives me a lot of different opportunities for analyzing those samples. And in fact, that large scale experiment is exactly what we need for investigating redox, because the way that we experimentally constrain oxygen fugacity, hydrogen fugacity, and redox state within these experiments is using this double capsule technique, where you can see within the very center of that capsule, we have our sample. And that's all enclosed in a little platinum container that's supposedly inert to other reactions. And then directly outside the sample, we have our redox buffer, which is our metal-metal oxide pairing that sets the oxygen fugacity. And again, all of that's enclosed in an outer platinum capsule. And this thing is pretty small. If you look at, say, the head on a pencil, it's about 5 millimeters. So this whole thing would sit on the head of a pencil very easily. That gives you an idea of how small it has to be to obtain high pressures. And also you can see here on the temperature oxygen fugacity graph, there's 3 different regimes of oxygen fugacity that I'm really going to be talking about. And that's going to be the more oxidized samples around nickel oxide, which represents more terrestrial Earth-like conditions. A somewhat reduced sample near the graphite buffer, which is moderately reduced. And then a very, very reducing redox region near the chromium oxide buffer, which, just to go back for a moment, you can see is approaching the solar nebula in terms of just how reduced it is. Okay, so bearing that in mind, I'm going to go ahead and start talking about the first study, which was on magma ocean crystallization and what happens to hydrous volatiles as the planet solidifies. And there's several things that we want to know from this study. We want to know the influence of pressure, the influence of temperature, the influence of oxygen fugacity and redox state, and then whatever else we can say about compositional variables. And primarily when I say influence, I'm talking about the influence on the solubility of these volatiles within the mineral and the melt, and then the partitioning of these volatiles between the mineral phase and between the melt phase. The second thing that we want to answer is which volatiles are present. And this is important because under different redox conditions, we actually expect water to speciate into perhaps a more reduced form, such as hydrogen gas. And equivalently, we might see carbon speciating between CO2 and methane. And currently today, we don't really have robust partition coefficients for very reduced systems. They've only traditionally been studied in very oxidized systems. So this is the first study to look at these partition coefficients in realistic magma ocean conditions as it crystallizes. All right, so to do that, I basically ran a whole bunch of experiments with different starting compositions at different pressures, temperatures, oxygen fugacities. But the big takeaway here is that I was running similar experiments in oxidized conditions, which are applicable to the Earth, to reduced conditions, which might represent these magma oceans. And here's what I found. So starting off, I started with some samples at lower water contents. That means I added about 0.2 weight% of hydrogen to the sample for reduced ones. And I will note that I didn't add the water as water. That is, I didn't get a syringe and drip it into the sample. What we actually did to get very reducing conditions was decompose thermally magnesium hydroxide. And so using that more reduced form of hydrogen, we're able to enforce a much, much lower oxygen fugacity. And this worked pretty well for the samples that didn't have a lot of hydrogen in them. You can see that we were able to synthesize very large olivine crystals relative to these kinds of samples and very large melt pockets, which are exactly what you want for analysis. Then things got a little bit more iffy when we upped the hydrogen content to above 1 weight%. Now, I mentioned before we use platinum capsules because they're relatively inert. They're not supposed to react with the materials inside the capsule. And their melting point is very, very high. So they shouldn't melt during these very high temperature experiments either, especially under pressure. But what you can see here is that the platinum is reacting. It's actually forming platinum hydrides, these little micro nuggets that can then infiltrate the capsule and contaminate the sample so that you no longer have large spaces of olivine or melt to analyze. And then when we get to 3 weight% of hydrogen in the capsule, things start to get really dire. And this might be expected. You're putting a lot of gas into a capsule and then you're heating it up. The whole thing is going to tend to destabilize, but we're really seeing widespread failure where the buffer, those other metal oxide pairings, are leaking into the capsule, contaminating the system. We no longer have a closed system. And those experiments are no longer very useful. So this gives a clue as to why these very reduced experiments haven't been run before, particularly with synthesizing minerals, so that they're not easy to run. And in fact, I think if research continues in this vein, they're going to have to come up with entirely new methods to run them. But I was able to get enough data that we can start deciphering some of those pressure, temperature, fugacity trends that we're interested in. But first off, I mentioned that these kind of experiments have been run before, particularly in oxidized environments for a long time, over 25 years worth of data, really. But the interesting thing to note here is that there still aren't very apparent trends when you're looking just for pressure effects, which clues you into the idea that there's probably many different competing factors, whether it's temperature, composition, redox, how these experiments were run, and some other parameter people haven't accounted for. So that's why it's important for me to elucidate pressure effects within my own samples, even if it's been studied before. And indeed, when you isolate one variable, you can clearly see that there is a positive effect on solubility with pressure, where both for the reduced samples given by those black markers and the oxidized samples given by the white markers, we see that as you increase pressure, as you go deeper into a planetary interior, you increase the solubility of hydrogen, and that is bulk hydrogen, into olivine. And we also see an impact on the partition coefficient, which is simply the ratio of hydrogen and olivine to melt. It also seems to systematically increase for both the oxidized and reduced experiments, holding all other factors constant. So that's exactly as expected. Pressure increases solubility. The next effect to elucidate is temperature. And here's where things get a little bit more interesting, because you would expect you have coffee, you have sugar, perhaps you're putting in your coffee, you increase temperature, you increase solubility. But actually what we see here is that for a given pressure, when you increase temperature, you actually decrease the hydrogen solubility. And this might be a little bit of a counterintuitive result. But the reason for this is simply that these crystals don't exist in a vacuum. They exist embedded in these silicate melts. So if you increase the melt fraction as you increase temperature, you actually decrease that hydrogen component, meaning that water activity decreases and you have less water available to infiltrate those crystals. So actually, again, this is a result that makes sense. And we can consider these experiments that I've run in context of the greater body of literature, particularly oxidized experiments, again, spanning over 25 years. I'm not going to show you the scatter plots anymore because at this point with this many experiments, it gets really difficult to tease out different correlations. It's a lot more instructive to just construct this correlation matrix where you can see which parameters seem to be correlated or anti-correlated. And of course, they all correlate perfectly with themselves. But you'll also notice that pressure is going to correlate with fugacity, and it also correlates with solubility of hydrogen and olivine. Pressure also weakly correlates with the water contents of the melt. And there's an anti-correlation with water in the melt and the partition coefficient. I also want to note for these experiments that it's kind of difficult to decouple the pressure and temperature variable, which is why you do see a weak correlation there. And that's simply because if you're synthesizing crystals, you do have to be in a somewhat narrow pressure and temperature range. It isn't possible to do this at any given arbitrary temperature and any given arbitrary pressure. So that's another complicating factor for how to run these experiments. Okay, so I've talked about pressure and temperature, and now I'm going to talk a little bit more about a lesser characterized variable, the one we're really interested in, which is oxygen fugacity. Okay, so looking at this diagram, I've put all the other studies and the few data points from my own study up, and then I've also put up another trend line composed entirely of my own data points. This is where things get a little bit interesting. Up until this point, it seemed to be that everything was falling on one linear correlation. But my work didn't. It's a bit out there. And I've already looked at pressure and I've looked at temperature, and they don't seem to be what's making it do this. It also doesn't seem to clearly follow oxygen fugacity in that some of the reduced experiments are on there. So that isn't the deciding factor, which really only leaves composition. I haven't mentioned that in the correlation matrix. It could be that I've simply created samples that are so bizarre, they're so not similar to anything else that they're making their own trend. So to look at that, I did a lot of electron microprobe work, where you can see I've characterized all the major oxide components of the melt and the minerals. And there's a lot of information up here, but there's really just 2 points that I want to pull out of this. And that's going to be that these samples are in equilibrium, which we can test through the partitioning of magnesium between the crystal and the melt. And this is well characterized in experimental petrology as a test for equilibrium of crystals. And sure enough, my data seems to match theory perfectly. So there's nothing too strange going on in terms of equilibrium. And then another thing that I can do is look at the melt polymerization, which is given by the NBO over T ratio, which is just the ratio of non-bridging oxygen to tetrahedral sites. And this tells you something about how condensed or how polymerized the melt is. Where 2.5 is considered a very depolymerized melt, and 0 is considered fully polymerized. But what's interesting to note here is that my values fall within values that are interesting in a planetary science context. They're between Morbs and lunar orange and green glasses. They fall within the range for Vesta. So I've actually synthesized glasses and crystals that appear to be working in equilibrium, and the glass isn't anomalous in a planetary science context. So it doesn't seem that it's the composition that's creating that alternate trend line. In fact, what's creating the alternate trend line is that I've run samples that are anomaly water poor. And I mentioned this before, that I had to get sub 1 weight% water to stabilize samples ideally. And in fact, most of the other previous studies that were oxidized didn't have this stability issue. So they were free to run samples well above 1 weight%, 2 weight%, 2.6 weight%. And in fact, melts can accommodate water well above 40 weight%. So my samples at 0.2 weight% are anomalously low in water, and that's what's making this difference. And in fact, once we account for the initial water content put into the sample, we see that these samples do indeed fall perfectly within an explanatory trend line. And this is also important because we don't necessarily know that magma oceans contained multiple weight% of water. It could be that they were only nominally anhydrous, in which case we desperately do need to consider the initial water content of these experiments. Okay, so I've answered the influence of pressure, we've looked at temperature, and I've shown that the oxidized and the reduced samples follow 2 distinct trend lines. We also see that the initial water content of the sample really determines how you interpret those trends as well. The next part I want to talk about is going to be which COH volatiles, since I've only really talked about bulk hydrogen contents that I've analyzed via SIMS. Now I'm going to see if we can't decipher which COH species we have in the melt. And perhaps this will explain why the reduced samples are different than the oxidized. So to start off, it's instructive to start with just basic fluid models. So that is absent again, all of the geology. Just looking at the equation of state modeling for, in this case, just OH. And what you see here is as you get more reduced to more negative oxygen fugacity, then water becomes diminishingly small in proportion. And basically the fluid speciates entirely to hydrogen. And what this means too is that my earlier correlation matrix was flawed when I considered oxygen, well, oxygen fugacity in terms of water fugacity, because we wouldn't actually have water fugacity at all if you get to an extremely reduced system. And you can see that given there on water fugacity superscript fluid. It actually drops to 0 in a sufficiently reduced system. And in fact, the important fugacity to consider is going to be hydrogen fugacity. And then I mentioned carbon before. So that was purely for system OH. We can consider the opposite end member in a carbon saturated system. And again, there's fantastic equations of state that we can use to do this. So here you can see for different pressures, 1 and 3 GPa. In a reducing system, you expect methane to actually be the principal carbon species and to be the largest proportion of hydrogen as well. Whereas if you have a more oxidizing system, you might expect to have solely water and CO2. So the question then is whether or not the melts that I analyzed follow these predictive fluid models. And the answer is yes, we do see evidence for this. So looking at the Raman spectra here, you can see on the top we have the more oxidized samples run closer to the nickel-nickel oxide buffer. And water is expressed entirely as that hydroxyl peak. We don't see any evidence of H2 or methane in those samples. But then once you drop too near the chromium-chromium oxide buffer, well below iron-wüstite, that's when we start to see hydrogen and methane become important reservoirs. So this does support a view of an early reduced magma ocean, primarily incorporating hydrogen and methane as volatile reserves for water. Whereas when the magma ocean progressively becomes more oxidized as the planet matures, that's when we might start to see speciation into these more oxidized species. But to summarize the important parts of this study, these were the first values for olivine solubility and partition coefficients in a very reduced system, where there's already been a lot of work done on glass. We haven't necessarily known how this affects crystallization. And we also see that we have systematically lower solubility and partition coefficients when it's reduced. And again, this is all important because we think that this might be a very prevalent stage in planetary formation and evolution. And it has very important implications for that early initial outgas atmosphere. All right, so the third part of the talk is going to be focused on something that's similar, but a little bit different, which is synthetic Martian basalts. And I didn't actually synthesize these. I got these samples from a collaborator who already published 3 papers on these samples. But the commonality between them is that these are realistic compositions of different analog Martian materials. Another very important thing about these samples is that they were run in graphite capsules, which you can see here on the SEM image, given that black surrounding the gray olivine crystals in melt. You'll also notice that the crystals are very large in terms of these kinds of experiments, perhaps. Some of them are even greater than 100 micron, so they're ideal for analysis. Another interesting feature of these experiments is that there was no water initially added to them. They were run entirely in Hydrous, because at the time that these papers were published, a dry Martian interior was a favored hypothesis. So water actually wasn't accounted for in these samples. They were supposedly entirely dry. And here you can see another wonderful image. And in this one, I do want you to notice that there's a lot more crystallites, which is one thing we're trying to avoid in these samples, nucleating around the much larger pyroxene grains, but still enough melt that they're analyzable. Okay, so they're in graphite. They're going to be carbon saturated. The first question is whether or not they look like the abundance of data run on melts in carbon saturated systems. And you can see that given here by the carbon solubility model from 2018. And sure enough, my experiments do look like they follow established trends in CO2 solubility and melts for moderately reduced systems. So that looks fantastic. The next question is, how is water being incorporated in the samples? So for pyroxene, there's a known incorporation mechanism within the crystal chemistry that correlates with aluminum, and that aluminum creates a hydrous point defect, and that's how water gets into the crystal. So because of the aluminum incorporation mechanism, you expect to see a correlation with water contents in pyroxene and the aluminum content of the crystal. And sure enough, we do. And we also see the same correlation in the partition coefficient. So this begs the question, can we do a one-step parameterization to calculate water in pyroxene crystals based on aluminum? Do you want to guess? The answer is obviously no. That would be a much shorter talk. But no, it turns out we can't. And you can't really see why from this image. But again, if we go back to the body of literature, we see one certain trend. However, when I plot my experiments on this graph, yes, they're significantly off trend once again. They don't look like anything that's ever been published before. But you can probably guess why, considering what I first told you about these samples. But essentially, they have extremely high partition coefficients. The reason why is because that solubility is not the only determining factor. The partition coefficient, of course, is a ratio between the mineral and the melt. And if you have a melt that's very, very low in water content, that's going to create a much higher value for the entire partition coefficient. So what we see here is that it isn't just aluminum and the incorporation mechanism of the crystal, but it's the surrounding water activity of the entire melt that establishes the partitioning trend. And once we take that into account, we can explain the data once again. And this is just for clinopyroxene, but in fact, orthopyroxene follows the same trend. For nominally anhydrous experiments, you get really high partition coefficients that can only be explained by the water content of the melt. Okay, so that's all really interesting. And if you're an experimental petrologist who works on partition coefficients, this is really exciting. But for the rest of us, you're probably wondering why we care about this. And the answer is because we can construct models that tell us something more interesting about the entire interior of Mars. So knowing that aluminum and knowing that the water content of the melt are important, we can construct a thermodynamically based empirical model that then can tell us the original magmatic water content. So this is the model that I've constructed. It fits really well for these kinds of experiments run over so many different years in different custom setups with different analysis techniques. And then we can apply that model to whatever clinopyroxene grains we have. And in fact, we do have some wonderful example of clinopyroxenes in meteorites, particularly in these Nakhlites, which are 1.3 billion year old samples that are minimally degassed too. So they should have a pretty pristine record of the Martian interior water contents. So by analyzing these clinopyroxene grains and then applying the model to it, we can back calculate the volatile content of those parental magmas, which in turn should tell us something about how the interior of Mars looks and whether it looks similar to the Earth, to the Moon, and perhaps to other asteroidal bodies. So fortunately, some other workers have already characterized the clinopyroxenes in these meteorites, where we have several different analyses done on different grains. And then applying the model to it, we can back calculate that original magmatic water content. And for my study, I've done the 2-parameter approach. Both the magmatic water and the aluminum were taken into consideration, where previous models perhaps have only used aluminum. And we do indeed see a large difference there. And I'm going to talk about this more in just a second, but we can use those magmatic water contents to then back calculate the mantle source water. And that's going to look like this, where you have to run some more models. And in fact, I've accounted for a variety of different scenarios here to try to get a realistic constraint on what the interior water content looks like. So I run equilibrium models and then fractional crystallization models of those different magma chambers. And that's characterized by the degree of melting in those chambers. So you can see that we simply progressively crystallize the sample and see how water is partitioned into the mantle or into those pyroxenes. And then also we need to consider different mineral assemblages. I've talked a lot about clinopyroxene and olivine, and indeed we do expect there to be a mixture of one or the other on the solidus, or liquidus rather. And then as it progressively crystallizes, you might get other minerals too, whether that's garnet or a mixture of orthopyroxene, clinopyroxene, olivine, and garnet. So these are the different situations that we need to consider: how it's crystallizing and then what is crystallizing. And as you can see here, using my new model, we obtain much lower interior water contents than the old parameterization just on aluminum, which systematically yielded much greater values. And that makes sense because that old model was only calibrated on samples that initially contained about 2.5 or more water content from the start. So they were very hydrous. And if you run a model that's only been calibrated on higher values, it's probably going to return higher values. But we don't necessarily know that the Martian mantle is very hydrated. So that's not an assumption we can make. And here's what the outputs of this modeling actually results in. So we see that the magmatic water content is probably going to be under 0.5 weight%. And this is only from clinopyroxene, but we can compare it to other melt water content estimates from other methods, such as apatite, directly from the melt, and so on. And it plots really favorably. It looks like most of the estimates are going to be under 1 weight%, and most of them in fact fall under 0.4 weight%. So this is starting to paint a consistent picture of what those parental melts might look like. And then finally, we can back calculate using those different models, the complete mantle source water, taking in consideration different crystallographies, different minerals, and different melting models. And sure enough, the new water contents are significantly lower than the old, probably ranging from around 40 parts per million up to perhaps a little over 100. And that's exciting too, because then we can consider those interior water contents within the greater spectrum of solar system objects. You can see the estimate for the Martian water content based on Nakhla falls relatively low, again, under 100 parts per million, but that is consistent with the lower water contents of the Earth, the primitive lunar mantle, and then also 2 geochemically distinct reservoirs within Mars, the depleted source and the enriched source. So it does look like this view of a less hydrous Martian interior is probably consistent with some things that we know about accretion, considering the moon as a more pristine, less geodynamically active body than the Earth. And then also it's in line with other estimates for Martian water content. Okay. So just to summarize everything that I've talked about hydrogen partitioning and solubility in very reduced systems. And I've talked a lot about different variables that affect it, whether it's magmatic water content, pressure, temperature, oxygen fugacity, and especially how melt water contents act as an important control for understanding partitioning behavior. Okay. Well, thank you so much for listening. I'd love to hear some questions.
Nakhlites, given that they are meteorites ejected from the surface rather than being actually representative of the surface, might not, the estimates made from them might not be very accurate for the actual Martian mantle?
Yes, absolutely. So I didn't do any of the processing on these papers, but I should mention that when they analyzed them, they weren't necessarily analyzing pristine crystals. I remember one of these papers, I want to say it was the Weiss paper, not 100% sure, actually rehydrated the crystals to get a maximum water content estimate. So that is built into the, to that starting point. But no, I agree. Those definitely aren't going to be entirely pristine samples considering they're on a meteorite and have probably degassed a bit. But one thing I will note here in terms of degassing and diffusion is that pyroxenes are a better candidate for these kinds of back calculations than olivine because they seem to degas less. So yeah, we could have, if I had applied the model to olivine, our numbers would be even worse.
Baptiste?
So I have two questions. That was a very cool presentation. So for your high pressure experiments, how fast do you quench the sample? Because that could be related to the number of crystals that you have in the sample.
Yes, I absolutely agree. So we do try to quench it as fast as possible, which is simply cutting current to the sample while maintaining pressure. And it's hard to say exactly how fast it quenches based on the thermocouple, but it does seem to be as close to instantaneous as we can get in these. So it's not that I'm doing a ramp down, for instance.
Yeah, okay.
From,
Yeah, I guess that was my question.
no, quenching is very difficult.
Yeah. And the second question I had was about the hydrogen incorporation. Do you know what is the site of incorporation? Is it just stuff in the lattice, or is it like some kind of is it replacing another atom or something like that?
Yes, so that is one of the big questions in hydrogen incorporation in olivine, and that we know for certain that there's at least 3 different incorporation mechanisms associated with magnesium, silicon, or the trivalent cation, so aluminum again. But for these studies, I actually excluded the trivalent incorporation mechanism, so aluminum, just to see if I could see a difference between the fluid activity. And as for how it's incorporated, that gets a little bit difficult too, because these samples aren't appropriate for fingerprinting incorporation sites like you might be able to do in a larger crystal sample with spectrographic studies. So it's kind of impossible to know. But I would say if it's H2, that's small enough to interstitially fit within the crystal structure. So that's very possible.
So would you say it would be interesting to do, for example, single crystal diffraction to get an idea if there is, like for the before and after the experiment to see like if you can see like a distortion in the lattice?
Yes, I think that would be really interesting. Or other spectral studies like IR, Raman on large gem quality crystals, that would be excellent.
Yeah.
Okay, any other questions? Don?
So it's easy to imagine the terrestrial planet would have multiple magma oceans. For instance, the Earth could have had a magma ocean early on, and then it solidified, and then the moon formed, and so you have a second one. Does that do anything? I mean, is there one-way street on any of this stuff, or could you ever tell the difference?
I feel like it's really difficult with the Earth since it's so geologically active that those original reservoirs just may not be analyzable.
Mars?
Yeah, Mars might be possible, especially because we already know that it has different geochemical reservoirs in the enriched and depleted source. So I think it's entirely possible that it might have had some kind of heterogeneous crystallization where you get different magma pockets where perhaps it wasn't completely molten and equilibrated at some point. Yes, I wouldn't be at all surprised to find that we had some more enriched sources and some more depleted sources.
Okay, any other questions? Are there any questions from the Zoom audience? If so, speak up. Doesn't seem like it. So let's thank Ardith once again.